All right. Hello, everyone. This is a recording of a presentation given just earlier this week. Actually, it was May 6th of 2025 in Novi, Michigan at the DTE ESD Energy Conference. Let's just jump right in. Um, my name is James Lydell. I work with DTE Gas. I work in a large commercial industrial gas group that helps large gas customers with their energy needs, and I'm an expert in CHP cogeneration, microgrids, and interested in all things decarbonization. I'm a mechanical engineer, formerly with Oakland University. I was there 16 years. I spent a big part of my career in building HVAC control systems and worked with DT Electric for a while on their energy partnership program on the Ford team way back when. Anyway, I am not an expert in data centers, but I do a lot of work with the large industrials, and it's a lot of infrastructure and HVAC cooling issues. So let's just get going here. It's a lot of good information. So basically, a data center is a large industrial site with a big process that uses a lot of electricity, and the infrastructure required, cooling and power, and potentially low carbon power is what we're going to talk about here. I'll talk about some estimates of new capacity growth and the infrastructure and decision factors where to locate a facility and the type of things to do for decarbonization, including potentially small modular nuclear reactors, because some of these sites are half a gigawatt in proposed size, but also low carbon fuels with conventional microgrids, and then talk about some cooling systems and how to manage cooling, thermal loads, and conclude with some case studies. So the grid was trying to decarbonize. We're moving towards renewables away from coal. And as we want to add all this new capacity for more data center, AI computing power, that is a challenge. It did happen with the cannabis and indoor grow boom for a while and Bitcoin mining, and now we're seeing an even larger required need of new electric capacity for data centers. And the infrastructure needs and the type of systems you put in might impact the power required and also the location of your facility. Liquid cooling is tending to be the efficient choice in future projects, and potentially with free cooling to reduce the need for mechanical chillers. Anyway, it's possible to make very efficient, low energy centers, and we'll talk about that. Like I said, I'm not an expert here, but I've tried to source a lot of these different slides. So at the bottom, you'll see a source on almost all the slides. There's a lot of different varying estimates of future required gigawatt capacity. And there's a lot of regional differences. Of course, Virginia, it's got a lot of data centers. And here's a 29 gigawatt estimate from Goldman Sachs, another McKinsey study with three different scenarios and up to 240 gigawatts required in the next less than a decade. So potentially a lot of power required. The anatomy of a data center, the conventional layout is something like this. You got grid power coming in. I'm not talking about water so much in this presentation. That could be a whole another presentation. But the efficient use of water or removing the use of water is something that's very important, especially when you're in a water poor environment. But mechanical cooling with evaporative towers is often the method of choice with layout of your data center and all the UPS system and backup power distribution and reliability, redundancy, and power distribution. That's all part of the game. So this is a typical layout. I'm going to talk a lot about the infrastructure here, very little about the computing efficiency. So the building and the site, access to energy, access to fiber network, uh, and then the energy supply, what options you might choose to be more or less carbon free, and then the on-site infrastructure, including backup power and cooling systems. And then keep in mind, this is a very electrical intensive process. So the computing efficiency and the amount of power towards the computers, I'm not going to talk about that because that's the process. And but that's a big part of data centers. Obviously, the computers are getting more efficient. If you wanted to dig into that, there are a lot of good sites to dig in deeper. hardware component design, virtualization of servers where you have multiple servers virtually running on one hardware platform, more efficient applications. They can often route data activity to different servers and different facilities, depending on time of day and power costs and maybe cooling requirements. So there's a lot of technology, of course, obviously in the computers themselves. But once you have the computer load requirements from the tenant or from the data center, then I'm going to talk about building the infrastructure around it. So the strategies for highly efficient infrastructure with cooling and power and types of power to get to decarbonized or low carbon solutions. So we're moving towards liquid cooling and often have an opportunity to not even use chillers and use free cooling with liquid cooling in the spaces. I'll talk a bit about that more later. We could probably spend a whole other presentation on backup power and resiliency. Obviously, like a hospital, a data center needs to be on 24/7. So the N+1, N+2 requirements, there's different tiers, tier 1, tier 2, tier 3. So you're going to need a lot of redundancy. Conventional diesel systems with on-site fuel stored is the way to go, I think, conventionally. But batteries are being looked at more and more closely. I'm not a big fan of the huge lithium-ion battery systems just because they're so expensive, but the price is coming down. But often flow batteries can be sized much larger. It's basically a strong and weak solution of a electrolyte that goes through a fuel cell type module, which can charge the liquid solutions or discharge and pull off power. So those are having a potential to be a large utility grade utility scale, large energy source, potentially for data centers. I'm also a fan of natural gas microgrids, so natural gas gensets could be an option as well. And hydrogen. Hydrogen is a fuel, of course, but you have to make it. So it's really a stored energy method, and it competes with batteries more so than it competes with other fuels because you do have to make it. So it's a stored energy system that's zero carbon. So that's worth considering. So let's talk about the infrastructure and where you might site a data center. You're going to need access to energy and labor, but data, fiber, and the data trunks are very important, of course. So, and then cooling, you might consider, land for solar and wind installations. Although a lot of data centers are purchasing power from far away off-site facilities with the PPA, power purchase agreements. But free cooling in northern climates is an option as well. So let's look at some infrastructure issues. I contend that there's three large infrastructure components to the United States, probably globally as well. But in the United States, we have petroleum mainly going to transportation for trains, planes, automobiles, and electric power industry, coal, gas, and nuclear, and then the natural gas distribution. And they all interplay with each other. Electric vehicles can displace petroleum, natural gas vehicles as well. But power to gas, where you make hydrogen, make some fuel from electric power. That's hydrogen typically. And of course, natural gas is used with cogeneration or CHP. And then the combined cycle gas turbine is the state-of-the-art new power plant. So these all interact. But now we're having a fourth network and infrastructure that's kind of becoming very, very critical. And that's what we're talking about today, data networks. I contend this fourth infrastructure is what we're constructing now and building out. So there are some sources. This is just a screenshot from an app that looks at data trunks, landing from ocean crossings and interstate travel of large data centers. So you're going to have to site a data center with access to one of these large data trunks. And then in the old days, we had these wall maps. I'm not going to provide too much detail here. I don't want to get us in trouble, but the utility, gas and electric are out there, and you're going to need access to one or the other or both. And in the old days, we had some of these maps. I had that one. This is from DTE, and it has electric and gas infrastructure. I mean, you're going to need a lot of power. So if you're putting in 100 megawatts, that's a small power plant. But some of these sites are looking at 500 megawatts, 1 gigawatt. That's a decent sized power plant. In Port Huron, DTE recently constructed a combined cycle gas plant, 1.2 gigawatts with 2 gas turbines. and a steam turbine bottoming cycle. The Blue Water facility, 1.2 gigawatts. That was a large plant. Some data centers are going to consume that entire power. Gas lines, you can go to a gas pipeline and contract for some capacity, and typically the data center is going to have to go back to a gate station that pulls the high pressure transmission lines down to a lower pressure, and that's an option as well, and putting power generation on site. But that's going to be part of your project development and location, as well as your cooling and the climate that you're going to have to address with your cooling systems. So all these things will take time to construct. There's permitting involved with power lines overhead and gas pipelines, of course, and the capital cost, both for the installation of the infrastructure and the operating cost should be considered. I contend that running a microgrid with gas-fired CHP or gas-fired distributed generation on site, with or without a lot of solar or maybe some wind, if you have that opportunity, that's going to be cheaper to run in time. It might cost more capital-wise, but maybe not. It depends on the electric installation requirements. If you have to come several miles and have 2-3 years to install some high voltage transmission lines in a substation, that's a significant cost. So it might be on par or equal to running gas to the transmission line, to the pipeline, and installing your own distributed generation on site. And in the long run, that will be cheaper to operate, almost in every case. And then the carbon intensity. If the grid power is using coal-fired power will make the grid carbon intensity go up, and you can beat that with natural gas on site or renewables or some mix thereof. So this is just a kind of a high level look at maybe a comparison between pulling grid electric and natural gas to your site for on-site power generators, whether they're gas turbines or fuel cells or reciprocating engines. But it all depends on the distance and the pressures and the available capacity in the networks at your location, at your chosen location. It's variable, so it's variable. But just to compare a little bit more of the gas and electric option, I'm from Michigan here. I used to live downriver, and driving up north to Oakland University every day for work, I would drive past the power lines on I-75 coming from Monroe Power Plant. Fermi, the nuclear plant, is a little farther south, but they have 3 generators there. So the transmission lines, the overhead transmission lines, which are pictured here, they, with full capacity, would be carrying approximately 1,400 amps, 850 megawatts each. That's about 3.4 gigawatts. So if the transmission line underground, protected underground at 600 psi, 30-inch line at 1,000 feet per minute, that's about 3.7 gigawatts of energy flow. And you can inject renewable natural gas or hydrogen into that, and it can be made somewhat renewable, just like the electric can be made renewable, although this would be coming from a coal plant here on the power side. So just obviously gas is a fuel, and to convert that to electricity, you're going to go through a power generation cycle that's going to lose a lot of energy. So electricity is much different than natural gas, but just kind of giving you a gut feeling of the comparison of the two. So you can get a lot of energy in a very compact and safe method with natural gas, and bringing that to your site might be more economical and faster and possibly less cost to construct. But we're also going to be looking at a big need for base load power from maybe some more nuclear. Here's a picture of Fermi 2 DTE facility down in Monroe, and there's small modular reactors are being chased by a lot of startup companies. The micro ones can even fit on a flatbed truck or a semi truck, and these are definitely going to be a solution for some data centers. Like DTE Electric, we have proposed to decarbonize by 2040. And to do that, we'll need a lot more renewables. We're one of the biggest renewable energy providers and installers in the Midwest United States. Solar and wind is a big part of it. But at some point, efficiency and maybe some more nuclear capacity will be required. So we're looking at small modular reactors as an option. Here's some artist renderings of some of the companies that are doing this. This Hitachi signed a contract with Ontario Power up north, just northeast of Toronto. So it's a rendering of a potential small modular reactor site. Another one in Virginia. that's being proposed to go next to a hydrogen hub with potentially a build out of a gigawatt of data center capacity in Middleburg, Virginia. So this is a project that's broken ground. It's called the Surrey Green Energy Center, both hydrogen production and data center. But these reactors, such as the NuScale Power module rendered here from an artist rendering, would be a 77 megawatt per module. The idea would be to put in like boilers at a boiler plant where you have multiple staged together, so, 4, 6, 8, 10 to build up your power plant. So here, 4 of them, 4 of these NuScale units is approximately 300 megawatts, just an idea of the scale. So the plant around that would be the cooling and the substation and the accoutrements to get a power plant online would be a number of acres. So let's look at that. Let's just suppose a 10-acre site would be sufficient for the cooling and the substation and the buildings, office space for your employees, and compare that running base load. But let's say 98% availability, they run pretty much continuously. You're gonna, on that small footprint, produce about 2,500 or almost 2,600 gigawatt hours of electricity per year, with 300 megawatts of capacity. 300 megawatts is the power capacity of wind and solar. A good wind site might be in the 40% capacity factor, or 35%, and that would produce about 920 gigawatt hours a year. And depending on your spacing, you're going to need about 3,000, 4,000, 5,000 acres. Of course, you can do other things around there. Farming and other things can be done within the wind farm, so it's not only wind, whereas solar takes up the entire footprint. So maybe 1,500 acres with typical construction methods, but 15% capacity factor in Michigan is what you're probably going to see, 14 and a half, 15. In the Southwest, you're going to get, in the 20s, and maybe in the desert, 30% capacity factor at the most, but just giving a comparison. So it takes a lot of land for these renewables. So if you want to add a microgrid with some renewable capacity, you better plan for some land. A lot of data centers are purchasing, a lot of these big companies, Google, Amazon, Meta, are purchasing power from an off-site facility, and they can either be renewable energy credits and just have the attribute purchased and then the power flow somewhere else, or a power purchase agreement, depending on your local regulations. You could potentially have the power delivered to your site. In Michigan, that's not, it's kind of like wheeling of power is not possible, but that's being done in a big way. I'm a big fan of combined heat and power systems where you put your own natural gas fired systems, whether it's a gas turbine or an engine or even a fuel cell on site, and that's compared to the grid. So they're all heat engines producing electricity, and if it's done far away, like the Monroe Power Plant, about 60% of that energy is thrown back to Mother Nature. The heat is rejected into Lake Erie or a cooling tower, and that's just part of the fundamentals of thermodynamics and when you produce power from a fuel source. But if you put the CHP system, the cogeneration system on site, you recover that waste heat for power or for cooling, and it's much more efficient. And if you use a lower carbon fuel, such as natural gas, it's the most efficient way to produce power. More efficient than a fuel cell, more efficient than anything else you can do. And then this whole system could be made net zero with renewable gases such as RNG, biogas, hydrogen, renewable ammonia is being talked about. And you can also make cooling from that heat. Absorption cooling is an option and is often done to produce thermally activated cooling systems. So this solution is viable, but I'm going to show you that a lot of the most efficient plants are not even going to use chillers, mechanical chillers at all. They'll use ambient cooling. So this is a very, very elegant way to operate. So the fuels of the future, I mean, I've even heard about renewable ammonia being a potential fuel, but typically you're going to use RNG. It's very expensive. It's made in modest quantities, but it's available in small quantities for big systems. Green hydrogen is produced from electrolysis. That's way too expensive to be a baseload fuel. But I think a big part of the future could be methane pyrolysis. That's natural gas being cooked or processed basically into hydrogen. CH4 can be split into solid carbon and hydrogen. So you have pipeline gas coming in, and on site you can produce your own hydrogen and make solid carbon, which has got a value. Uh, Graphite, graphene for battery production. And most of our battery graphite comes from China, from mined mineral sources, natural sources. So making a synthetic graphite or even graphene, which is a future magic uh, building block for a lot of neat things. Graphene would be amazing if we could make it from methane pyrolysis, and also carbon capture from the exhaust. Let's see, in the on-site presentation, I did not show these examples, but let me show you a couple of examples of what these look like. I contend, and this is very conventional, so I can show you how to design a green hydrogen system. Give me a call. It's very scalable from 5 kilowatts to 5 megawatts. You can make hydrogen from electricity. If you make it from solar and wind, it's green hydrogen. If you make it from nuclear, they call it pink. But it's very expensive. The electrolyzers can be PEM or alkaline-based electrolyzers. And then you have a green, clean, zero carbon fuel that can be blended with natural gas or burned straight into an engine or a turbine or used in a fuel cell. So this is very doable, but very expensive. Even with the tax credits, it's very expensive, and you're not going to have an economical solution with green hydrogen for a large power plant. Pyrolysis, on the other hand, is when you use natural gas. And yes, you're using natural gas, and you use more of it because it's making coal. It's like a coal mine in reverse. So you're going to have carbon black, which is about a quarter of the mass. So CO2 is about 75, it's actually 76% oxygen, and it's a gas. So you have to compress it, liquefy it, either put it in a pipeline or a truck and get rid of it, somehow sequester it. But if you make carbon black, it's carbon forever unless you burn it. This could be put in tires or asphalt. It's a saleable, valuable product. And if you make graphite, which is another form of carbon black, graphite is even more valuable. Graphene is even more valuable. It's stronger than Kevlar. I mean, it could be superconducting and make wires out of it. So that's the future uh, material is graphene. And this whole process is being chased by a lot of companies. You can't go to anybody to buy a commercial system off the shelf today, but a lot of pilot programs, a lot of pilot projects are being installed by many, many companies. I've got a whole other presentation on methane hydrogen production from different sources and talk about methane pyrolysis. It's also a YouTube video. The most conventional way to make hydrogen today, also expensive, but this is more within reach of an economical solution, is natural gas SMR, steam methane reforming. So steam methane reforming is often in very, very large plants. And if you just vent the carbon dioxide, they call it gray hydrogen. That's what most hydrogen is produced from, natural gas with no carbon capture. Capture the carbon and they call it blue. So you can get perhaps 90, 95% carbon capture if you go all out, and that's a blue hydrogen, low carbon solution. But then you have all this CO2 to deal with, but the hydrogen can be burned in an on-site system very cleanly with no carbon at the point of use, but you do have to contend with all the carbon coming out. And for 1 MCF, 1,000 cubic feet of gas, I've shown the mass balance there. Or you could just put the carbon capture on your power generation. Forget the hydrogen and just go ahead and utilize your natural gas and capture the carbon on your boiler or your power gen system, and that's very conventional as well. A lot of companies have solutions for this, and this is going to be a big part of our future. But it's not cheap. You might double the cost of your system by adding in the carbon capture. CO2 has a value as well. I mean, if you can make it food grade, you can sell it. But there's also tax credits for carbon capture. A whole nother discussion. But so let's get into the data centers themselves. So a lot of metrics you can talk about. The one that's often used in the industry is PUE, power use effectiveness. Unfortunately, it only talks about the infrastructure in relation to the data center load itself. So the computers and the computing, let's say it's a 300 megawatt data center, how much more power do you need to support that? That's what the PUE stands for. I'll show you what it looks like. The reciprocal and efficiency number is this other measure, DCIE. This will be a percentage, and the PUE will be a number greater than 1. But I like the net zero energy, net zero carbon, and if you talk about the data center itself, somehow you want to measure that. But PUE is used all across the industry, and I think it's a limited measure looking at the whole complex, the whole data center. But we'll talk about PUE today. That's what most folks use to compare data centers, and it looks something like this. So you have the total energy of infrastructure plus the computers divided by just the computer energy use. So it'll be a number greater than one. So in the past, 2, 3 was a common measure. So the whole site would be this level of efficiency. Average today might be more in the 2 range. Very efficient, getting down closer to 1. You'll never get to 1.0 because that means you have no infrastructure at all. But maybe 1.05 ultra efficient data centers. That I think that's possible. And how do we get there? And what kind of savings might you have from something like that? Well, baseline, if you're using 8-cent power, let's say you're getting grid power from your microgrid or the local utility at 8 cents a kilowatt hour, a 2.0 PUE means a 300 megawatt data center is going to use 300 megawatts more of base load energy coming in. So that gigawatt hours per year is here, and that's the baseline. So if you drop that down to 1.5, you're going to save about $100 million a year. Drop it down to this ultra efficient system, and you're going to have to add a lot of capital cost to get there. I'm going to have to do some things to make that happen, although I'll show you that maybe it's not as bad as it looks. That's potentially a $200 million per year savings. If you're getting a great deal from your utility company, you're only paying 4 cents or 5 cents, that's going to erode this savings, but just give you an idea of what we're talking about here. A little graphic that's kind of fun, showing what Google shows as their PUE measurements. So the data center itself might be the calculations here, or you could look around the whole site with the losses of the transformers and the substation and some other losses. So they call it a comprehensive PUE, but just give you an idea how they measure that. And from a online reference, you can see that the PUEs have been coming down. A lot more attention has been paying to efficiency. So this is from 567 respondents to surveys of actual data centers. So we're getting down below 1.5. We're getting down to 1.5 or so. But let's look at a EPA estimate of a more average 2.0 data center. So the IT load is half of the total, and then the cooling is often the biggest component. But electrical equipment, your power distribution units, a little bit of lighting, some fans and pumps, and transformer losses, they make up the bulk of the rest. But the cooling is often the most dominant. So let's talk a bit about cooling. You might even want to locate your data center to an area that has the ability for free cooling. And there are some data centers being sited in northern climates to take advantage of more days of cold air. Here's a site in northern Norway. I'm sorry, Sweden. Metas Lula. I don't think I'm pronouncing that right, but a case study of an example is a proposed site of a gigawatt. HDR Engineering rendered this gigawatt proposed site in northern Norway, where they would have all the fjords with the hydropower and wind power producing 100% renewable for this site. And there would be no mechanical chillers. Also, they talk about underwater. That's a bit more far-fetched. I think maintaining these sites and the environmental constraints with salt water and and the danger from storms and things would be challenging, but there are some people testing it. Here's a Microsoft test of a small data center, and they're continuing, excuse me, they're continuing with some further testing. YouTube video link there I shared with you. This is some photos from that. The Chinese are not far behind, or maybe even more advanced with this. This is a test of a high cloud data center with 400 servers submerged in ocean water. So thermal management is important, and typically it's done with air. You have chillers, mechanical chillers, and chill water to PTAC units or Liebert units that are in the data center. For the smaller systems, and bigger systems are obviously designed differently, but you have hot aisles and cold aisles. In the management of the air, raised floor with the fiber in the network, and then cabling is under the floor with the cooling. That's a very conventional way that they've been doing it in the past. Then managing the hot air and getting it out is the way to optimize. But now we're looking at some servers. I should have had some specifications from some suppliers of servers where they're warranting the servers to go up to 100, 120 degrees. So allowing the space to not be at 70, 72 or 80, but to go up to 90 degrees or 95 degrees. That might be an option, and that would allow you to use outdoor free cooling with no chillers for more hours of the year, or maybe all year. So that is being done now, and I'm contending that that's probably the future of the most ultra efficient chillers. There's some debate about whether over many years that the servers will have a shorter lifespan. Of course, they have to be reliable. That's number one. You have to have a reliable system. But I've been talking to some developers of Bitcoin mining, and those little server modules that do the Bitcoin mining, they're not as expensive, and they have so many of them, and they have so many running 24/7. And if you lose one, it's not the end of the world. You just lose a little bit of your Bitcoin capacity. So they just allow the temperatures to rise to the 100-degree range or more, and just let your system work with no chillers. That does cause concerns for human maintenance and technicians going in to manage these locations. And here's an article if you want to look at data center knowledge for this reference. This Belgian center, I think it's 10, 15 years ago, they were running one of the most efficient data centers in the world with no mechanical cooling. So the question about OSHA requirements and heat and how you manage your personnel, you can't have a personnel working for many hours in a data center that's at 95 degrees. Similar with the greenhouse or other systems, so you have to take that into account. But this system, if it got too hot, they would just for a few hours a year apparently would reroute network traffic to other server facilities, and that was how they maintained this operating with no mechanical cooling whatsoever. So liquid cooling will be a solution, I think, of choice. This is from an ASHRAE, an NREL presentation. It shows the difference between forced air cooling with air movement versus water movement. Water is a much better heat transfer media, so you can carry a lot more energy and provide a lot more cooling or heating, but we're talking about cooling here. It's less pumping, less, a fan, of course, as for air, and a pump is much more efficient at delivering the fluid than the BTUs of cooling to the end use. And better heat transfer, a lot less area required. So liquid cooling is the way to do it in the future. And whether you bring that liquid to the server or to the chip or to the room, in the past they'd have liquid cooling chill water to an air conditioning unit in the room, but now we're talking about bringing it to the rack, and then that'll be distributed directly to the chip. So they have these immersion cooling options that I've seen, where you have a liquid bath, not putting it in the ocean, but putting in a liquid bath. That's being proposed, and there's some companies looking at that. Here's a illustration, a photo of a liquid cooled chip motherboard, and the racking systems where you have water distributed to the racks. Basically, you'll have the process water like an industrial plant, and then that water, whether it's chill water or I'm contending just free cooling ambient water, it doesn't have to be 40 degrees. It could be 70, 80 degree water, depending on the application. But then they have a little heat exchanger inside of the rack. That heat exchanger will then distribute a closed circuit with these little dripless disconnects. And it's a little scary thinking of all the liquid tubing inside there, but it's being done. And NVIDIA, one of the biggest chip manufacturers or data server manufacturers in the world, is migrating towards liquid cooling as their most efficient solution. Here's a Hewlett-Packard solution. So water cooling really is the future. Here's a fun little illustration of a two-phase, so like a refrigerant-based fluid that would be bathing the computing equipment, and then that would boil, and it enhances your heat transfer. The heat transfer is much more enhanced with the two-phase flow. And then once the fluid comes out, the vapor comes out, then you have a heat exchanger and pull the cooling away from with your processed water. Here's a couple of photos of some conventional facilities. So you got a substation up here in the top left. You got some cooling towers here, and all your cooling modules or generators. I'm not sure which side's the generators. So you get backup generators and cooling modules, and then around the perimeter. So this is very, very typical. It's a Google site. I was in Las Vegas for a conference in March, and driving by on the highway, I saw one of these sites. I forget what number. There's many, many, many of these switch data centers in Las Vegas. On the south side here is the generators. On the north side, they have their own proprietary air conditioning modules. Very signature red color, and then a substation here from the utility grid substation on the right side. Case study. We're moving towards the end of the presentation here. I've got a case study of a fairly modest size data center. They're saying it's a 10 megawatt size data center at the ESIF, the Energy Systems Integration Facility in NREL, National Renewable Energy Lab in Golden, Colorado. I actually visited it a few years back when I was still at Oakland University, and they have a PUE that's down in the 1.06 range. So they're making it happen. No chillers, and some water cooling, and I'll share a few photos of that. So you are using some pretty advanced technologies, but the cost savings from no cooling towers and no chillers might be substantial. Here they do have evaporative towers, but you could have dry coolers. I mean, if you have a body of water or a lake, a river, I mean, you could potentially be using that for your cooling source. Here's an illustration of what they have going on. So they pay a lot of attention to their thermal management on the hot aisle, cold aisle. But let's see, here they don't actually distribute the processed water to the rack. Looks like they're producing cold air and then managing the rack thermally from the air side. I think the future will be bringing the liquid directly to the rack. But they do have a thermal siphon system that reduces pumping power, evaporative towers when needed, and dry coolers when they have it available. So there are some, they call them adiabatic cooling towers that have a dry cooled closed circuit that then spray water on the outside only with limited hours of the year. So there's a lot of HVAC cooling innovations that make these things more efficient. But no mechanical chillers and liquid cooling to the rack, I think, is the future. Here's an aerial view. The data center's in the middle. They have an office center and a laboratory as well, but 10 megawatt data center that's ultra efficient. It can be done. Here's a screenshot of their HVAC data screens, and you can see that they are running where they propose to be. So getting the job done. A couple of years back, I visited out there when this facility was just being commissioned. Just throwing these photos in here for fun. They were just commissioning the building, and they had a lot of neat things out there. But I was visiting NREL for a broader tour, and this was just coming online. There's a picture of the pumping systems and heat exchangers. I will conclude with kind of a futuristic vision of a data center that really, it depends on where you're located. So I would say try to either manufacture a body of water or put it next to a river or large body of water. Like if you're in, like downtown Chicago uses Lake Michigan water for their district cooling system. I mean, that's a great option, a river or a lake, or you can just put in a pond system. I mean, a geothermal where you drill in the ground, that can be designed as well. At Oakland University, we have a platinum rated LEED certified platinum human health building, and that is a 400-ton geothermal system. But the pond system, like Saginaw Valley, they've got a very large, also a human health building, a couple buildings attached to a very large pond that was naturally occurring, and they put tubing in there to have a closed loop system. But a microgrid, on-site generation, could use natural gas, could be using some hydrogen as a storage system from maybe some on-site renewables. So you can make hydrogen when you have excess solar or wind. That's unlikely to have excess unless you have a lot of land. But this is the kind of vision of what you can do depending on how much land you have and your climate, and then your cooling options. So this is my vision of a highly efficient, potentially net zero or near net zero data center solution. In summary, um, this is possible. I think liquid cooling and technology enhancements to make liquid cooling more efficient inside the data center, and then reducing the need for mechanical cooling with free cooling from outdoor natural temperatures, and allowing that data center environment to rise into the 80, 90 degree range, and then using everything else you can do to make your computers more efficient. And then look at carbon capture and net zero fuels, low carbon fuels. Renewable natural gas is expensive, but you can blend in some renewable natural gas with natural gas. Anyway, there are some solutions. I hope you got some thoughts going here, and um, the plan was to just throw all these different current technologies at you and plant the seeds of possibility. Thank you for your time, and I hope you had fun. Thank you.